It's helpful to compare the double and single bonds. So the number of atoms attached to a carbon is affected by the number of bonds. If we only have single bonds, we're going to have 4 carbons, and it's going to be a tetrahedral arrangement, and there'll be 4 groups attached to the carbons. Here, if you have a double bond, then it only has 2 other bonds that it can make with something else. So you're going to have 3 things attached to the carbon, and it's going to have a different geometry. It's going to have a, it's going to have a trigonal planar geometry. Rotation around that double bond we saw was relatively free. We had the eclipsed and staggered conformers, but around the double bond it's restricted. We can't get any rotation around that. The geometry, we've got different conformations. Staggered is preferred, but they all rotate among themselves. The geometry of the double bond is planar, it's flat, and I'll show you a model of that in a minute. The bond angles will be different because of the number of groups. This is 109.5, that one's 120. And the bond length is different. A single bond is longer than a double bond. When you think of a double bond as sharing 2 pairs of electrons, that pulls the atoms closer together. It also makes a double bond stronger. So let's just look at a double bond real quick. In the model kit, we use the long flexible gray sticks to make the double bond. And we can see that it is the 2 carbon atoms, and whatever is attached to them all lie in a plane. And so it's planar, and we get this 120-degree trigonal planar shape. And you can't rotate because there's 2 bonds there and they don't swivel. So we don't have any rotation.